All right. Hello, everyone. Welcome back to Data 100. We are on lecture number 9, I believe. In the middle of the third week of class. It feels like a slow Tuesday, so I do have a new topic for you guys on dimensionality reduction, and it is quite a change from the previous weeks of lectures. Today's lecture will be mostly mathematical, about linear algebra, and you'll find that starting today, for pretty much the rest of this course, the lectures will be more and more stats and math oriented. Because at this point in the class, you guys have gone over most of the tools you need to actually do data analysis, or at least you have the experience and kind of the know-how, hopefully at this point in the class, to learn new tools or like pick up new tools as you come along, or as you notice tools that may be useful to you. And so now returning in this class to a set of mathematical tools that we use to analyze data. One of them is dimensionality reduction. Okay. Just to remind you guys that homework 2 is due tonight. Make sure, as always, to turn in both the OKPy and the Gradescope, and do make sure that both OKPy and Gradescope are turned in on time. So if you turn in your OKPy on time and turn your Gradescope on time, I make no guarantees about your grade for Gradescope. Okay, so do make sure to turn in both on time, which means give yourself like maybe a few extra minutes to turn it in if you're like scrambling to finish at the last minute, which I know I was when I was a student. But it's better not to do that. It's better to turn it in as early as possible. Okay, so homework 3 is due this Friday. If you haven't started yet, I suggest you look through it because it's fairly long and involved. We have a midterm next Tuesday. And on Monday, instead of lecture, we're going to have a midterm review session. 2 of my TAs will be leading it. They'll be going through some practice problems and answering some questions from you guys about the midterm, and hopefully it'll be useful for you when you're reviewing the content. Okay, and small group tutoring this week, I had a link yesterday, but that link was wrong, so you'll want to use the link that I have on the slides today if you're interested in signing up for small group tutoring this week. Okay, let's talk about dimensions. So we've talked about the number of attributes in a data table, and we've talked about how a data frame in Pandas has a set of rows and a set of columns. What we haven't talked about is the fact that sometimes those columns may contain data that's unneeded or redundant based on other data that's in your data table. For example, this particular table has 2 columns, one for age and one for height in inches. So these could be observations of people. And this table here has the same data on people, but it has an additional column for height in feet. And you'll notice that the height in inches and the height in feet are kind of redundant to each other. If you know the height in inches, you can find the height in feet. If you know the height in feet, you can find the height in inches. And to kind of capture this idea that sometimes you have redundant data in your data table, we use the term dimensionality and the number of columns differently. So the number of attributes or the number of columns in a data table, we'll just say are the number of columns. But when we say the dimension of a data table, we'll refer to like the minimum number of columns you need to describe the data set. Okay, so in this case, the top data set has a dimension of 2. But the bottom data set also has a dimension of 2, even though the bottom table has one more column than the first table. All right. And so we use, since you guys should have been taking or have taken linear algebra before, this should feel familiar to you. Basically, the idea here is that we can use linear algebra terms to describe dimensionality. Okay, so we have the number of attributes is the column count in our data set, but the dimension of a data table or a data matrix is the rank of the matrix. In other words, since the feet column is a linear combination of the inch column or the height in inches column, that column kind of disappears when we reduce that matrix down to echelon form, and because of that, the bottom matrix still only has rank 2. Because it only has rank 2, we say the bottom matrix has dimension 2. Okay, so even if I had a 4th column on the bottom table, and let's say I had the 4th column for some reason be like the average of days and height in inches, that bottom table would still have rank 2 because that fourth column would be a linear combination of the first 2 columns. Okay, so the term linear combination refers to taking a multiple of a column and adding it to a multiple of another column or subtracting, right? And the idea here is that if you can use a linear combination to describe columns, other columns in your data table, then you don't need to store those data in the first place. If I drop that third column off the bottom table, I would still have all the information in my data set. I would just represent it using less space. Okay. This is important because we often come across what we call high-dimensional data in the world, where, for example, in genomics, you might have one row be a person, and every column in the data set be, let's say, like their DNA base pair at that position in their DNA sequence. Okay. So if you do that, I believe the human genome has like 7 million base pairs. Correct me if I'm wrong, if there are any biologists here. But if you structure your data matrix in that way, and you have 100 people in your data set, then what you're going to have is 100 rows in that data matrix and like 7 million columns, right? So that is some like really high-dimensional data. And in reality, you come across high-dimensional data more often than you think. And so the question here is that how do we deal with high-dimensional data? One way to understand high-dimensional data is to try to visualize it on a scatter plot. But the problem here is that a scatter plot can only display 2 dimensions. You can try to make a 3D scatter plot, but it's really hard to interpret. If you try to make a 4D scatter plot, you should talk to me because we can probably talk about like writing a paper with you and like using it as a case study for something. But basically, visualizations are more or less limited to 2 dimensions at a time. If you use like hues and faceting, you can maybe show a few more. But really, like the visualization techniques that we have are kind of limited compared to the high-dimensional data that we can encounter. There's no visualization that can effectively visualize 7 million dimensions at the same time. Okay. And so we can use what's called a scatter plot matrix to discover associations between attributes. But oftentimes what we want to do is figure out whether the observations cluster together. Okay, so what we want to do is we can try taking our data set, and if it's like, even though it might be 7 million columns in our data table originally, what we can do is try to reduce a number of columns to maybe 2. And if we can reduce the number of columns to 2, then we can plot them on a scatter plot and try to find some patterns that we wouldn't have seen otherwise. Okay. So so our goal here is to take observations that have many columns or many attributes, or many number of columns, and try reducing the number of columns to 2. Of course, if the rank of your data is larger than 2, then you will lose information. I'll talk about that in a little second. But our goal here is to try to say, okay, well, if we're going to lose some information, but let's try to keep as much information as possible. If we can keep as much information as possible, maybe it's the case that even though we're reducing the dimensions to 2 dimensions, we can still capture the patterns in the data. And so that's kind of the goal of today's lecture and tomorrow's lecture. Okay, so our first idea for this might be to pick the 2 variables with the highest variance. Our end goal here is to build up to what we call principal component analysis, or PCA, where instead of picking just the 2 variables or 2 columns with the highest variance, what PCA will do is try to like combine some columns together in order to find like the best, to create some feature combos that capture some variance in our data. But first, let me go through the first idea and show you what this intuition is. Okay, so I have here the slides, and I have here the code. All right, cool. All right, so I'm back with the legislator data that I worked with from lecture 4. So I have here, oh gosh, all right, run this code. I have here some cells. I'm going to run this cell to read in the legislator data. This code should be familiar to you. I believe it's the exact same code as I was working with, I believe 2 weeks ago, 1 week ago. And we see here the legislators in Congress. Right? We have here the party. We have here the birthdays, so on and so forth. Last time we talked about looking at the ages of these Congress people. This time what I want to do is look at their voting patterns for bills in Congress. All right, let me zoom in. Okay, so I have here a data set containing the Congress people's votes. Okay, so this row says the member A00374 for session 1 of the House voted no for this bill. Okay. And so what I can do is merge the two tables together. I won't go through this today because you should know how to do some data manipulation. And what I'm going to do here is I have one row for every member of House, for every vote that this person did for a particular bill. And I'm going to create a pivot table. Okay, so this pivot table says for Bill 66, this member voted yes, and this member voted no. This member voted yes, so on and so forth. Okay, so I have here one column for every bill in my data set, and one row for every member of Congress in my data set. Okay, and you can imagine a world where I didn't actually know about the existence of Democrats and Republicans, and you can imagine a world where I just give you a data set that looks like this. Okay, so you have here like some people or some observations, and you have here some like data on those people or data on those observations, and you want to find out some structure in this data, right? So you might want to uncover the fact that there are like these political party differences based on their voting patterns for this particular data set. Okay, so you might imagine that, for example, if Bill 66 was like super Democratic, then all Democrats would vote yes and all the Republicans would vote no. But that might not always be the case, right? It could be like, what you might want to do is look at a set of 4 bills that are all like Democratic or like lean towards the Democrat, like what the Democrat Party likes. And you might imagine that in general, right, the people who are affiliated with the Democratic Party will vote yes on those bills, but the people that are affiliated with the Republican Party will vote no for those bills. So what you might want to do here is figure out, okay, well, I have some people and some observations. I want to figure out whether I can group or cluster together these people somehow in some meaningful way. Okay, this sort of matrix appears more often than you think. For example, on Amazon, you have Amazon reviews, and then you can also create a table that looks very similar to this one, right, where every row here is a user, and every column here is a product, like an Amazon product, and every value inside this table is the stars they gave to that product. You can imagine like Netflix has like users and movies, right? And you can have a table saying like whether the user liked the movie or not. Okay, and so you might want to figure out, or Netflix might want to figure out, okay, I have some people here who watch like, I don't know, Avengers. They watch like, oh gosh, I'm like super blinking. Mission Impossible. Like they watch like, I don't know, some other movies, right? And then they might say, okay, well these people seem to like what we call action movies. So we'll give them some more action movies. Other people seem to like sci-fi movies, so we'll give them like Interstellar, for example. Okay. Okay. Oh my gosh. All right, so our first idea for reducing the number of dimensions of this table. So for example, this table has 22 columns. And the first thing we might want to try is look at whether there are columns that have high variance. Why do we want columns that have high variance? Well, because if we have here a bill that everyone voted yes on, that's not going to help us distinguish whether a person is a Democrat or Republican, right? We want a bill where like it caused a lot of tension or like dissension within the Congress people, so we can figure out whether people like wanted yes for this bill or no for that bill. And the way we can measure that like kind of dissension is by the variance, because the higher the variance, the more different the votes are for that particular bill. Okay, so I can find the variance by asking NumPy to calculate the variance for every column in this table. If I set axis equal to 0, it'll calculate the variance for every row. Okay, so I have here, every column. So I have here the variance of column with label 66, variance of column with label 67. I can sort these values. And I can see here that the bills 80 and 69 seem to have the highest variance of 0.25. Okay, so that might tip me off that maybe I can visualize those two columns and see whether that reveals any structure in the data. So we can try to plot them. Plot these points here. Let's plot column 69, column 80, put in our vote pivot table. All right, so what happened here? So that's not very meaningful. Why do I get a scatter plot that looks like this? Yeah, right?
Yeah, so all your values are either 0 or 1, so that's just the 4 different combinations you can get, like 0 and 1.
Yep, so these are discrete data points. And in particular, every value in this data set is either 0 or 1, which means that these points here are all the people that voted no for both Bill 69 and Bill 80. This point up here is the people that voted no for 69 but yes for 80, so on and so forth. So I have here like a 2D scatter plot, but all the points are on top of each other because all the points are either 0 or 1. I can try to fix this by adding some noise. Okay, so I can do vote pivots. Could try to add some noise to this. I believe we have a jitter option. I don't know if scatterplot has jitter. I was hoping not to do it myself. Yeah, currently non-functional. Thank you, Seaborn. Okay, let me try doing lmplot. And I have here x jitter, y jitter. So let's do x jitter equals 1, jitter equals 1. And I don't want to fit the regression line. Okay, that didn't work. I apologize. All right, so I can do it manually by adding some normal noise. Oh my gosh, okay. Sadly, my code is cut off here, so I'm going to just steal from my completed notebook. All right, here we go. Bam, let's do that. Okay, so I've added some noise. It doesn't seem to have helped too much. So I see here like some clumps, and I see here some clumps, but you know, it's kind of hard to see some structure in this data. I could color the points by their political party to see whether the points are actually separated here. But if you do that, you won't really see that much new information because all the points are kind of on top of each other. I could add more jittering. But really what I want to do here is again, not just rely on 2 columns of my table. I want to figure out whether there are combinations of columns that can let me separate out the different types of voting patterns in my data. Okay, so here I'm kind of throwing away all the columns in my data set except for 69 and 80. And what I can do instead is figure out some clever way of combining columns together to get some meaningful new columns. Okay, so let's talk linear algebra. So linear algebra is actually useful for things in real life. Skip this. Despite what you might think at first, I know when I first learned linear algebra, I definitely thought what's the point of putting numbers in a box and adding numbers together? But it turns out that linear algebra is surprisingly useful. And I'm gonna try to give you some of that intuition today. Okay, so remember from all the way back from homework 1, right? We had here the Berkeley fruit bowl problem, where we had $2 for apples, $1 for bananas, and $4 for melons. And we had fruit bowls. Okay, so we had 1 fruit bowl with 2 of each fruit, 5 apples and 8 bananas. There were some more fruit bowls, but I'm only doing 2 today, just for the sake of space. And what we did was we put those prices in a vector. A vector is essentially a matrix with only 1 row or only 1 column. In this case, this is a column vector or a matrix with a 3x1 matrix. Okay, so I have here on the left a matrix that describes the fruit that's contained within each fruit bowl. And when we multiply these 2 matrices, or when we do this matrix vector multiplication, we magically get out somehow the prices of every fruit bowl, right? And the reason why this happens is because one way to look at matrix multiplication is to think of one matrix as your data and the other matrix as like some operation or some computation, and the matrix multiplication performs like some computation on data. Okay, so for example, I have here the dollars and the fruits from the previous data set. And so the first matrix you can see is the number of fruit in each bowl. Okay? The second matrix, or second vector, is the dollars for each fruit. And so when you multiply those two matrices together, you kind of like do the unit conversion, right? You go from fruit per bowl to dollars per bowl. And the way you do that is through this matrix vector multiplication. And in particular, you can't just do any computation you want. Matrix multiplication encodes a very specific type of computation, which is called a linear operation. A linear operation here, okay, so if I add a new bowl here, I can add a new row to my data matrix. If I add a new row to the bowls matrix, I'll get a new row in my vector output. Okay, so for example, if I wanted to add more computations on the same data, I can add new rows to my left-hand matrix. Okay, so matrix multiplication encodes what we call linear operations on data. Linear operations, like the name, so if you imagine like the y equals ax plus b linear equation, linear operations are essentially that, but on everything except like everything in your data set. So for example, here we have this matrix multiplication performs like something times x plus something times y plus something times z, and then we add all of them together. Okay, so it's either going to be multiplying by a number or adding a number or adding terms together. So either multiplying by a constant or adding things together. Those two combined essentially perform everything that we call like linear operations. Okay. So one thing you may have noticed if you're learning some linear algebra is the fact that like you need the middle dimensions to match. So for example, the matrix on the left is 2 by 3. Okay, so we say 2 rows and 3 columns. The matrix or the vector on the right is 3 by 1, which means it has 3 rows and 1 column. And the resulting vector has a dimension 2 by 1. Okay, and so my question to you is let's try to think about the intuition behind these numbers here and why the middle dimension seems to disappear when you perform the multiplication. Okay, so I'd like you to talk with your neighbor now and try to figure out why does a middle dimension need to match? Okay, so don't say something like it just needs to match because the matrix multiplication says so. You should try to like make sense of it. Okay, so just say something like related to something about data or computation, or related in this case to like fruit bowls or like fruit prices or something like that. Okay. For questions 2 and 3, I want you to think about what it means to add a new row to the left-hand matrix and what it means to add a new column to the right-hand matrix. Again, don't just say something about matrix multiplication, like multiplying new numbers together. I want you to say something about fruit bowls and fruit prices. Okay, go for it. Okay, hello, let's bring it back. So I was informed that my mic turned off before. Is my mic on now? Can you guys hear me in the back? Microphone's on? All right, sounds good. All right, so why does a middle dimension need to match? Any guesses here? Anyone have a good explanation or like something that's more intuitive than multiplying some numbers together? Sure. Name and response.
David.
Hi, David.
You need the middle number from that, or else if you have just that number, you can't add and multiply it because like in the computation, if you look at 2 columns instead of 3, and you have 2 by 2, you multiply 2 times 2 is 2 times 1, but then you would end up value multiplied by 4. Therefore, you couldn't have a complete value.
Yeah. That's certainly one way to look at it. So David says, okay, if I drop a column from computation matrix, then I can't do the computation on my data vector. Yeah, I think that's totally valid. One way to look at this is you can think of the computation here as like a function, right? So in Python, you write functions that take in a certain number of arguments. In this particular case, you can think of the number of columns in the computation matrix as the number of arguments for your Python function, right? So if you have a function that says like, that has like 3 arguments in it, if you try to give it 2 arguments in Python, Python will complain at you and say this function actually needs 3 arguments. And in the same way, the number of columns here needs to match the number of rows on a data vector because the middle dimension of these 2 matrices refer to kind of like the input dimension for a particular computation, right? So if my function here needs 3 arguments, then I need to give it 3 arguments. If it only has 2 arguments, I can only give it 2 arguments. And that's why the middle dimension needs to match. It's just another way, so you can talk about it as though it's about multiplications, but one intuitive way that I particularly like is this kind of view that one matrix is about a verb, a computation, or operation, and the other matrix is about data. Okay, what does it mean to add a new row to a left matrix? Well, I would say that adding a new row, I kind of gave away this answer on my previous slide, but I would say that adding a new row to a left-hand matrix is adding a new computation or adding another bowl, right? Another fruit bowl with some different fruits in that fruit bowl. What does it mean to add a new column to the right matrix? This is a little bit harder to interpret, but I could say something like adding a new column here is like adding a new store with different fruit prices, right? So if I add a new store with different fruit prices, I can perform this matrix multiplication, and I'm going to get the prices for the first store and the prices for the second store as a second column in my resulting matrix. Okay, so there are interpretations for these matrix multiplication things, and it's handy to know them because it helps you not only like remember all the different like little, all the little tidbits that go into linear algebra, but it also just helps you like appreciate it for its usefulness. Okay, so I'm going to write these down. So for number 1, so the number of arguments for computation needs to match. Okay, for number 2, adding a new row is like adding a fruit bowl. And for number 3, it's like adding a new store with different fruit prices. Okay. So again, for another diagram, for another like pictorial view of what's happening, or a good way of looking at this matrix multiplication, I have here like a matrix on the left multiplied by the matrix on the right. And if you look at the matrix on the left as operations and the matrix on the right as data, then one way to look at it is to say, okay, all my data come in columns, right? So I have on my right-hand matrix, every column is another data point. And on the left-hand side, every row of that matrix is another operation. And when I do the matrix multiplication, you can imagine kind of like pouring the data through the operations to get out some new data. Okay, so that's another reason. You can imagine like if you like kind of take the matrix and kind of like pour it on top, the number, like the height of this matrix needs to match the width of this matrix. Another like kind of like visual way to think about this matrix multiplication. All right. Now I'm going to stretch your minds a little bit, and you may not notice that matrices and vectors just contain numbers. And because they just contain numbers, like there's no one saying that the left matrix is always a computation and the right matrix is always data. Because of the symmetry in this matrix multiplication, you can also see the left-hand matrix as data and the right-hand matrix as the computation. What does it mean in the context of the fruit bowls problem? You can think of the first assignment of, so if you think of computation as a left-hand matrix and you think of the data as a right-hand vector, then you're doing what we have done in the previous few slides where we say, okay, the operation here is calculating the overall prices of fruit bowls by looking at the prices of each fruit and multiplying by the number of fruit in each bowl. If you look at the left-hand matrix as data and the right-hand matrix as the operation, then you're saying, I have some fruit bowls, I'm going to assign those fruit each a price, but the result of both those views is the same because you're calculating the overall price for each fruit bowl. It's just a matter of like your perspective. So you can kind of take this matrix multiplication, you can have different perspectives on the same thing, and those perspectives tend to come in handy, especially later on when we're talking about like weird perspectives on different matrices. Okay. So basically the takeaway here is that you can interpret a matrix many different ways. The most common interpretation we're going to use in this class is that one matrix holds data and the other matrix holds some operations. But we're going to use either the left-hand matrix or the right-hand matrix as our quote-unquote data matrix. And you'll see me switching between these different perspectives throughout this lecture and throughout tomorrow's lecture. For example, one other interpretation is that one matrix holds coordinates in like a two-dimensional plane, and another matrix can hold a transformation of coordinates. So for example, if you have an image, you can do a special type of matrix multiplication to rotate that image if you're doing some image manipulation. You'll use matrix multiplication a lot if you take a computer graphics class, and because what they do there is that they say, okay, like when I'm looking in this direction at this particular wall, then that's a vector from my eye to the wall. And if I turn my head, I have a new vector pointing outward from my eye, so that's a transformation using a matrix multiplication. Okay, so many uses for linear algebra. Hopefully you guys will see more. Like basically, it's pretty hard to really wrap your mind around the usefulness of linear algebra until you see multiple different reasons for using it. And in this class, I'm going to try to show you one reason to use it. But as you go along in your data science career or basically if you're working in science, you'll probably work with linear algebra at some point, and hopefully that'll give you some more perspectives on why it's useful. Okay, I did want to give a quick plug for 3 Blue, 1 Brown's videos. If you haven't seen those videos, they're like extremely good. I was contemplating just showing like 5 of his videos instead of giving a lecture today, but I decided to give a lecture today instead, and you can watch his videos at home. Okay, let's talk about matrices in Python. So in Python, we can work with matrices too, as you guys have seen a little bit in homework 1. In Python, a matrix is a 2-dimensional NumPy array that only contains numbers. We can do some useful operations on matrices. For example, we can take the transpose. So I can call matrix.t to transpose this matrix. I can also take a linear combination of rows of the matrix. I have here the original matrix. I note here that the bottom row, or let's see here, the middle row here is just the average of the top row and the bottom row. I can show you how that works by taking out, taking out the first row, adding it to the second row, and dividing by 2. Like so. And you can see here that the middle row is a linear combination of the first row and the bottom row. An alternative way of looking at this is The bottom row is a linear combination of the first row and the third row. It just requires some like algebraic manipulation for you to see that those things are equivalent. But basically, one row here is quote unquote unnecessary, and that unnecessary row is unnecessary because it's a linear combination of the other two rows. Okay, so one other way I could write this is I could kind of make this product bigger. So I can write 0.5 times the first row plus 0 times the second row plus 0.5 times the third row. And this is the same thing, and you may ask me, why am I doing this 0 times the middle row? And the reason why I'm doing 0 times the middle row is because I can put those numbers into a vector. And I can perform a vector matrix multiplication to do the same thing. Okay. So in this case right here, I have my matrix is my quote unquote data, and my vector here is actually my operation. The operation says take half the first row, none of the second row, and half of the third row and add them all together to get a new row vector. Okay. Here we go. So I have here my matrix. One sad thing about NumPy is that it doesn't have a good way of representing column vectors. So in NumPy, both row vectors and column vectors are one-dimensional NumPy arrays. And what that means is if I want to take the matrix here and perform this matrix vector multiplication, I don't do like this weird vertical NumPy array thing. I have to give it a one-dimensional NumPy array. So it's a sad fact of life, but you should just get used to it in that even though it looks horizontal, it's actually a vertical. Like NumPy will treat it as a vertical vector because it appears on the right-hand side. So I get here, so I have 3 by 4, and I have 4 by 1, which means my final result is 3 by 1. And this here is actually another column vector, right? So if I'm doing it on paper, I would definitely write these numbers as column vectors because I'm doing like this. I had 3 by 4 and 4 by 1, so I have 3 rows in my final output and 1 column in my final output. But NumPy will just display it as a row because that's NumPy. Okay. So this is what's called a right multiplication. I can also do a left multiplication. I can take an array, as I showed you before, and I can add a matrix. And this at here says do a matrix multiplication or matrix vector multiplication. So I don't use the time symbol to do this. The time symbol does something different for matrices. I want to use the at symbol. All right. So let me give you some questions here. All right, so in this example, I have here the ages and height data set that I had in the first few slides. And I'm going to ask you to interpret what the operation on the right does to the data on the left. Okay, so I have here data. I'm treating the matrix on the left as my data. I'm treating the matrix on the right as my operation. And I'm asking you to interpret the result of the following matrix. You can either do this computation by hand, or you can try to use Python. But go ahead and stare at that for a few minutes, talk with your neighbor about it, and see if you can come to some interpretation of what I'm doing here. Okay, let's bring it back together. So if you actually perform this operation, or if you do it in Python, you'll notice that the result looks like this. Okay? And I would interpret the result of the final matrix as the same data set as the original data set, but with an additional column where the height is in feet instead of in inches. The reason why I did that, the reason why I can say that is because I have here, right here is what we call the identity matrix, which keeps the original data the same for the most part. And I have here one more column on my operations matrix that says take 0 of the age column and 1/12 of the height column and add them together. So this essentially says my third column in my resulting matrix will be 1/12 of the second column in this matrix. Okay, what if I wanted to find the average of the first 2 columns of my original matrix? What would I put in my right-hand side matrix? I'll put 1/2 in the top row and 1/2 on the bottom row, because that says take 1/2 of the first column and add it to 1/2 of the second column. Okay, so more interpretations for you. One more question. So you've measured the width, length, area, and perimeter of 100 backyards. What do you think the rank of the resulting matrix is? And if you think the rank is less than 4, construct the matrices to recover the data matrix. Okay? And so what I mean by that is, right here I have a data set with 4 columns. And if this data set has a rank that's lower than 4, then I can write something similar to what I did on the previous slide, where I decomposed the right-hand side matrix into the multiplication of 2 smaller matrices, right? And I'm saying that we can do something similar for this data set if the rank is less than 4. So why don't you stare at this and talk it over with your neighbor for a few minutes. All right. So how many of you guys think the rank of the matrix is 1? How many of you guys think the rank of the matrix is 2? How many of you guys think the rank is 3? How many think the rank is 4? All right. So the rank of the matrix is 3. The reason why it's 3 is because even though area is a function of width and length, it is not a linear function or a linear combination of width and length. Okay, so to compute the area, I multiply width by the length, but doing that is not a linear operation. On the other hand, perimeter is something like 2 times the width plus 2 times the length, and that's a linear operation. Okay, so in this case, the rank of the matrix is 3. And what I can do is I can keep the width, length, and area columns, multiply them by that matrix to get the result of the final matrix here. So what I'm saying here is that I need the first 3 columns, width, length, and area, and the 4th column in my final matrix is 2 times the width plus 2 times the length, and 0 times the area to get the perimeter of each rectangular plot. Any questions about this? Okay, so again, a linear combination of columns is all you can do with matrix multiplication. You can't multiply columns by each other. You can't take the square of columns. You can't take the log of columns. You can't take the square root of different columns using just a matrix multiplication. All right, let's take a break. All right, I think the form is open, so we'll come back in 3 minutes. Okay, I'm going to close the form now. Is anyone still filling out attendance? Raise your hands. Otherwise, I'm going to close it in 3, 2, 1. All right, it's closed. Okay, so we've gone through some linear algebra, try to give you some intuition on matrix multiplication. And now what I'm going to do is introduce a few more building blocks, and then I'm going to build up those building blocks to get to something that we call the singular value decomposition. All right, so we say that two vectors are orthogonal if they meet at a right angle, or if the dot product of those two vectors is 0. Okay? The length of a vector is the square root of the dot product of the two vectors. So when you dot product two vectors together, when you dot product the two vectors together, you get a single number. And if the vectors are orthogonal, then that dot product will be 0. If you dot product a vector with itself and take the square root, you're going to get the length of the vector. And you can prove that doing the dot product in that way is the same as doing the Pythagorean theorem of like square root of a squared plus b squared. So taking the length of the vector using the dot product is the same as doing like the Pythagorean theorem that you're familiar with from high school, hopefully. Okay, so the unit vector has length 1. And we can extend the notion of orthogonality to what we call orthonormality, where orthonormal matrix has columns that are all unit vectors, they're all length 1, and all the pairs of different columns are orthogonal to each other. So what that essentially means is that all the columns point in different directions, or directions that are perpendicular to the other directions in that matrix. Okay, so if a matrix is orthonormal, okay, so it's not orthogonal, I say orthonormal matrix and orthogonal vectors. An orthonormal matrix has the inverse of the transpose of an orthonormal matrix is its inverse. Okay, so usually you have to do some crazy manipulation to get the inverse of a matrix. But if your matrix is orthonormal and square, then you can just take the transpose of the matrix and you get the inverse of the matrix. So it's convenient. And another way of looking at an orthonormal matrix is a rotation matrix. The reason why we can think of the matrix as rotation is because all the columns are unit vectors. And so when we multiply, when we do a matrix multiplication using an orthonormal matrix, you can think of it as rotating the columns of your data. Okay, so for example, if I have these two vectors up top, I have here, you can think of these as like maybe like 5, 0, right? And like 0, 5. Okay, so I just have two vectors here. If I multiply by an orthonormal matrix Q, then the vector lengths will be the same, but they'll point in different directions. And in particular, if the orthonormal matrix Q moves this vector down to the bottom, then it will move the top vector by the same degree. Okay? So it'll rotate the my entire collection of two vectors here by the same angle. That's what an orthonormal matrix does. The inverse of an orthonormal matrix is a transpose. So if I take the vectors on the bottom, multiply them by Q transpose, I'll recover the vectors on the top. So I can take vectors, rotate them, and then unrotate them by multiplying by an orthonormal matrix or by its transpose. Okay, that's one piece. My second piece is on diagonal matrices. That wasn't supposed to show up until the end, but I'll spoil the result for you. So basically, if you have a diagonal matrix, and usually in this class we'll usually use the term sigma to refer to this diagonal matrix. The sigma term here refers to a matrix, and if the matrix is diagonal, then what you're computing is not really like a full linear combination of all these vectors. You're just going to take multiples of the columns on the left. So if I have here a sub 1, a sub 2, a sub 3 on my diagonal, the resulting matrix will just be a sub 1 times the first column, a sub 2 times the second column. It's not going to be 0.5 times the first column plus 0.5 times the second column. It's just going to be multiples of the columns in my matrix. So each term here refers to the multiple of the column on the left. That's what a diagonal matrix does. One common diagonal matrix is the identity matrix, right, where every value in this diagonal is 1. And the identity matrix multiplies each column by 1, which means that all the columns are left the same as they were before. It does nothing to my original data. Okay, so another way of looking at a diagonal matrix is an operation that scales coordinate vectors. All right, so what that means is if I have these two vectors on the left-hand side and I multiply by sigma, I could get either a stretching or a shrinking of my two vectors, or I could get a reflection if one of the values here is negative, right? So if I have -1 in my diagonal for this particular vector, then that vector will get flipped over to the other side. It'll be a reflection. If I have 2 on my diagonal, then this vector here will get stretched out by a factor of 2. If I have 1/2 on my diagonal, it'll get shrunk by a factor of 2. Okay, so an orthogonal or orthonormal matrix rotates, a diagonal matrix scales. Okay, and now we can go. Now I can talk to you about the singular value decomposition, which says that any matrix with rank R can be written as a product of three sub-matrices, or 3 smaller matrices. And we call that matrix, we call the original matrix X, and we'll say that you can write X in terms of the product of U, sigma, and V transpose. U and V are orthonormal matrices, and sigma is a diagonal matrix. And if you can find the right matrices to do this splitting up of X, then we call that the singular value decomposition. So the singular value decomposition is kind of like this operation that you apply on X to decompose it into 3 smaller matrices. Okay, so one important thing to note here is that the rank R is not always as big as the number of columns in your matrix, right? So if I have here 1,000 columns, but I only have rank 2, then this diagonal matrix here, sigma, will be very small. It will only be a 2 by 2 matrix. Similarly, the matrix U here will be very narrow, right? It'll be like, if I have here 100 observations, then it'll be 100 by 2 columns here in U, and this VT matrix will be very flat, right? It'll be 2 rows by n columns. Okay. Another way of looking at the singular value decomposition is by remembering that U and V are orthonormal, so we can see them as rotations, and sigma is diagonal, so we can see it as scaling, okay? So basically, because of this decomposition, the singular value decomposition theorem says that since you can decompose any matrix X into the product of those 3 vectors, you can view any matrix X as applying the 3 operations one after the other. So if I take the matrix X, if I do X times V, where V is a vector, then what this decomposition says is X is going to take that vector, rotate it, scale it, and then rotate it once more. So when you multiply X times a vector V, you're going to get, if I had these original vectors V1 and V2, I multiply by X or I multiply by A, they're going to end up over here. So I'm going to have this as my resulting V1 and this as my resulting V2. But in reality, we can decompose that transformation into a single rotation, scaling, and then a final rotation. Okay. So this all the pieces that I have. And it turns out that this decomposition is really useful because we can rewrite that expression up top, X equals U sigma V transpose. And what we can do is right multiply by V. So I'm going to take both sides, multiply by V. Now, on the left-hand side, I'm going to have X times V. On the right-hand side, remember that V transpose V is the identity matrix because V transpose is the inverse of V because V is orthonormal. So that means that the V transpose over here will disappear when I multiply by V on the right-hand side. I'm going to get X times V equals U times sigma. Why is that useful? Well, because X times V has dimensions n times R. Okay, so that means that if X is 1,000,000 columns but only has rank 2, X times V will only have 2 columns. Similarly, the left-hand side is equivalent to the right-hand side here. So these two, you're going to get the exact same matrices on the left-hand side and the right-hand side. So both of these matrices will be m, number of rows in my original data, times the rank of my original data set. And that rank is always equal to or smaller than the number of columns in my original data. Okay. So essentially what we're doing here by doing this multiplication is we're expressing x in a reduced dimension form. Because the rank of a matrix is oftentimes or can be smaller than the number of columns in the matrix, so we've expressed x here in terms of a smaller number of columns. We perform dimensionality reduction. Okay, another way of looking at this expression is, again, we can treat one matrix as data and one matrix as an operation. So I can read the left-hand side as either rotate the points in x so that they're axis aligned, so to speak. So what that means is I'm going to treat x as my data and v as my operation. I know that v is orthonormal, which means that it's a rotation matrix. So x times v is a rotation of my original points in x. Or I can read the right-hand side as I have directions in u, and multiplying by sigma scales those directions, right? Because u is orthonormal, which means that u has some directions, but all those directions are unit vectors. They all have length 1. And sigma says scale those directions so that they match, roughly speaking, the magnitudes of x. So x is not like this unit. X is not like, doesn't have unit vectors inside of it. But if you multiply u by sigma, it'll match, so to speak, the magnitudes in x. So it's a very hand-wavy, intuitive way of looking at it. I'm just trying to give you some more perspectives on this expression here that I have. Okay, let me show you what this is in Python. I have here a matrix. And I can compute the singular value decomposition by using NumPy, which is very convenient. You can do it by hand. You might learn this in a linear algebra class, but I'm not going to do that in this class because that's a pain. Okay, so I can print. Let's print the shape of u. I can print the shape of v, and I can print the full matrix S. Okay, so S is our sigma VT. Okay, so I see here that my original matrix was 3 by 4. So my U matrix is 3 by 3. My V transpose matrix is 3 by 4. And my S diagonal matrix has 3 elements in it. Now, when you compute the SVD in NumPy, it will give you the sigma matrix as a single vector, but you can expand that vector into the diagonal matrix by using the diag command. So if I do np.diag of S, then I'm going to get the diagonal matrix here. Okay. Now, you may notice here that this row here is a linear combination of the first row and the bottom row, right? If you remember, the middle row is the average of the first row and the bottom row. And because of that, the rank of the matrix is 2, not 4. Okay? And the rank of the matrix is reflected here in NumPy by the number of non-zero elements in my vector S. Okay, so I have here a vector S with 3 elements, but one of them is 0, which means that you have one row that's a linear combination of the other rows. Okay, similarly here, when I take the diagonal, I see here that one value on the diagonal is 0, which means if I take u and multiply by diagonal vector, by the diagonal matrix sigma, I have here a column of all zeros. So the right-hand column here is all zeros, which means that I can drop it from my matrix without really serious repercussions. And so the difference between the way NumPy does it and the way that I had it on my previous slide is, let me go back here. Okay, right here. On my previous slide here, I had the sigma matrix as an R by R matrix. So I'm doing the compression, so to speak, here by reducing the size of the sigma to match the rank of my matrix X. In NumPy, it will not get rid of the 0 for me, but I can get rid of it myself. So I'm going to do that now. I can get rid of this by saying that U is equal to this matrix, but only the first 2 columns of it. Okay. Similarly, I have here V transpose. And I can do a similar thing to V transpose, where I can get rid of the bottom row of it without any problems. So I'm going to get rid of the bottom here. Okay, so now I have here the matrix that matches the rank of my original matrix X. Okay, so I have here U, I have here sigma, and I have here V, VT. Okay, I can also get the top right corner of this, so I can do sigma equals, and I'm going to take the top right corner. Here is my S. Okay. Okay, so remember that the matrix U is orthogonal. So I have here orthonormal. If I do U at U dot transpose, I'm going to get the identity matrix because it's orthonormal. Okay. Similarly, the V transpose matrix is orthonormal, also the identity. And all I can do now is compute the expression matrix my X times V. Okay, so the left-hand side of my expression on my most recent slide, I can do X matrix at V VT dot T. So my matrix V is VT dot transpose. I can do matrix at V. This gives me a column of all zeros. I can also compute the same thing by doing U at NP dot diag VT to recover my original matrix. Okay, so the decomposition recovers the original matrix, and when I do matrix times V, I'm going to project or reduce the number of dimensions in my original matrix. So I have here one row for every point in my matrix X, but I have fewer columns because this column here is all zeros. Okay. I believe I can do that. Yeah, so I have V is equal to V. I reduced the number of columns before. Okay. And so what is SVD useful for? Well, one reason why it's useful is because if I have points like this and I plot them, you will notice here that if a column is a linear combination of other columns, it's quote unquote unnecessary. And the reason why it's quote unquote unnecessary is because in this example here, I have here y is a linear combination of x, and you can see that all the points lie perfectly on this line here. Which means that even though I had 2 columns in my original data set, I don't need 2 dimensions to think about this data. I can just if I just kind of tilt my head, right, I see all the points going on a single line. It's really one-dimensional data, but put into a 2-dimensional space. Okay, and I can use singular value decomposition to reduce the number of dimensions of this data. So I can do U SVT, and I can take the SVD of the points. Okay, and I can copy up here my command. Take that, paste it here. Okay, so I had here 30 points. I had here originally 2 dimensions, but one of those dimensions is unnecessary because one of my values in S is 0. What I can do is compute the projection of X onto this lower dimensional space. So I can do, on my side I had X times V. I can do X times V by doing points.values at vt.t. Okay. So what this does is it computes the projection of x, but using a smaller number of columns. It does a dimensionality reduction, and you can see here that I only need one dimension to represent all the values in x. What does this mean intuitively? Well, what we can do is note that the V matrix is a rotation matrix because it's orthonormal. Okay? And so what I can do is take the first direction of rotation for VT and show that to you. So I can do x direction, y direction equals the first row of VT. So I have x deer, y deer. They're negative right now. Just for plotting purposes, I'm going to make them positive. But it's the same direction. And I can plot them by, let's see here. I'm going to not type all that code in and instead cheat. Okay, I'm going to pull this piece of code. All right, so I have here my original points, and on the points I plotted the first direction inside of V. You'll notice that the direction inside of V is the same direction as the points. Okay, so V transpose has the directions, quote unquote, of my original data. And so if I want to make the points, so what I can do is try to rotate these points so that they lie on a flat line, and that way I only need one column of numbers to represent those points instead of two. Remember that V is an orthonormal matrix, V transpose is an orthonormal matrix. I can multiply by V to do the unrotation, to do the derotation. And that's what I'm doing when I do x times V. Okay, so V transpose is this direction, which means I'm multiplying x by V performs the inverse rotation. It rotates back these points onto a flat line. So what I'm going to do here is, oh my gosh, I have to make a new variable. I can compute the projection of x as, I can do points.values at vt.transpose. Again, this one is a 2D vector, but I can only work with the first column of points, so I'm going to take out that first column here. And these are my points projected into a one-dimensional space. I can plot those points. And I can see that when I use singular value decomposition to reduce the number of dimensions, essentially what it's doing is getting rid of this unnecessary 2D chart and making it a one-dimensional data set. Okay, so it goes, in this case, I'm going from 2 dimensions to 1 dimension by doing a rotation. If I had 1,000 dimensions, I can also reduce them to 2 dimensions in the same way by using singular value decomposition, because it just performs a general reduction of dimensions. Okay. So I'm going to give you a preview of PCA, which is what we're going to do tomorrow. PCA is a specific technique that uses SVD as a component of it. And what it essentially does is we use it to reduce the number of dimensions to 2 dimensions. So I'm going to compute here the PCA. I'm going to plot for you the projected members of Congress. Okay, so I have here the members of Congress. And remember that the original voting patterns was like a 20-column matrix. And what I've done here is use PCA to project the members of Congress into 2 dimensions instead of 20. So I've done dimensionality reduction. So I can plot all the members on a 2-dimensional scatter plot. And what's interesting about the scatter plot is that I noticed 2 clumps. So this is just from voting patterns, right? I'm not making use of any political party affiliations. I'm not making use of what states these people are in. I'm only using the voting patterns of the members of Congress. And if I plot this and I color the points by their actual political party affiliations, then I see here that somehow PCA has put all the Democrats on one side and put all the Republicans on the other side. I apologize for the color scheme, but my point here is that there is some structure in my voting patterns, right? Even though I had 20 columns there, I don't actually need all 20 columns to uncover the structure of political party affiliation. Instead, I can look at their voting patterns and use PCA to reduce the number of dimensions, and I can uncover the structure in my data that way. So even if I did not know, for example, that I didn't know about the existence of Republicans and Democrats, I can still clump people together by using PCA and reducing the number of dimensions in my data just by looking at the voting patterns of people. You can imagine a similar technique being used, for example, to cluster people together for the movies they like or the products they like. There's many applications of PCA. Okay, so I'm going to get here tomorrow, but essentially you can know that using SVD, it's like most of the way there, and then PCA is just a couple extra steps onto SVD. Okay, so in summary, we see matrix multiplication as an operation. We can reduce the dimensions of high-dimensional data in a specific way by using PCA. One component of PCA is singular value decomposition, and that SVD gives us small matrices when the rank of X is small. All right, I'll see you tomorrow.